So today we will take two important questions, and that are related to the sizing of your inverter or the designing, which is very important because as a designer you need to size your inverter, and the second is about the delay. And these two are interlinked because the sizing will affect the delay of your inverter. So why this question is important for an interview? Because as a designer, as a digital designer, you would be doing many such kind of sizing when you are doing designs. And if you have the insights in the inverter level, how it is working there, then probably you can just extrapolate that knowledge to any circuit. So that's why this question is very important if you are going for any digital design profile. So let's get started. Know from our previous discussion that if this is our inverter and this is our output node and this is our input node, and here we have a capacitance which is CL, the load capacitance. And we already know from our previous discussion that whenever we are charging our this load capacitance, charging means in the output we need a high voltage. That means in the input side we have provided a zero logic, right? So whenever we provide a zero logic, our NMOS will get cut off from the ground and our VDD will get connected to the CL, to the load capacitance, through the resistance of our PMOS. And that resistance have some formulae, as we had our ID expression current through a MOSFET, and also we have the voltage around that MOSFET. So probably it's very easy to find out the equivalent resistance. But today that is our not concern, like of finding that equivalent resistance formula, and for the purpose of interview also it's not so important. So right now just assume that yeah, we can find out that. So this circuit is nothing but just a RC circuit, right? And if you just remember your concept of RC circuit, and there the charging time it will take, the delay tau would be 0.69 R equivalent P and the CL. Now many of you, I'm sure you probably don't remember this formula. It's all okay, you don't need to derive it at right this moment. You are going for interview, not an exam, so no need to derive it. Probably your interviewer might ask some question around it, but it would be if he is interested in analog domain. But for a digital profile, probably he will just skip, or if you say no, I can't remember it right now, it's all okay. So the time to charge this CL through this R equivalent is given by this formula, right? And this is nothing but your delay of from going low to high. Our output was at low, but we are charging it through VDD, and that is nothing but this one, 69 R equivalent P and your CL, right? And same wise, if we design for the NMOS when we are discharging our CL load capacitance, so that time we will call it TP from high to low, and that is also same 0.69, and that time R equivalent of your NMOS will come and the CL. So from this we can roughly say, yeah, to make our inverter work super fast, we just need to reduce our CL. That could be one option, or hey, reduce the R equivalent or R equivalent of your P or NMOS. So if we can do one of these two things, our inverter will work very fast. And why we want a very fast inverter? Because the lesser the delay, the more the faster inverter, imply more logic could be computed inside a small amount of time. For example, if your inverter have a delay of 1 nanosecond, right? So 1 nanosecond imply the maximum rate of operation it can perform in 1 second would be 1 by 1 nanosecond, and which would be roughly 1 gigahertz. So that means any signal which is faster than 1 gigahertz, your inverter will fail. So that's why we need a faster inverter. And in the sense we are talking about inverter, but inverter means all the digital circuits, right? For example, nowadays we have 5 gigahertz processor. So how we achieve this thing? By minimizing this delay, we achieve that thing. There are many other aspects I'm not going through. So now we want to reduce our CL, right? And we need to reduce our R equivalent N or R equivalent P. But to reduce them, we need to know their physical sense, their actual dependency on MOSFET properties. So in MOSFET, what we have? in our hand. We have W by L. For a digital designer, L also sometimes fixed. We have only W, and then we have our VDD, like how much VDD we want to give. Anything we have in our hand? Probably not. These things only we have. So now we need to actually want to know that what are the sources of CL, the load capacitance first. So let us first try to reduce the CL, and then we'll see if we can reduce our R equivalent also. To know the sources of CL, the capacitance, we need to quickly go through or brush up our capacitance which are there in our MOSFET. And how we have a capacitance in our MOSFET, because this is your MOSFET and here you have your diffusion area, here you have your gate, and from here only you can see your gate, and this channel is actually forming two layers. So we will have some capacitance here, parasitic capacitance here. This gate is overlapping your drain area, your source area, so this overlapping capacitor would be there. This diffusion region, it's nothing but your PN junction. Like for example, it is N plus, so it is P. So here we'll be having a PN depletion region. Here also we'll be having a PN depletion region. So here also we have the capacitance. So your MOSFET is actually full of capacitance or parasitic capacitance, and due to this capacitance only we have the delay mainly. So we need to study those things in detail if we have time, but now we don't have time. We need to prepare for interview. So roughly or quickly, if we go through those capacitance, this diagram is your a back-to-back connected inverter, so that we can appreciate the CL, from where the CL is coming. So here we have a CL, and here also we have a CL. But let's see about this thing. So this CL mainly is coming due to this capacitance, this wire capacitance, and then this external capacitance. What are those? Those are C. So these are your diffusion capacitance from the inverter 1, and these capacitance are due to your drain and the body PN depletion region, this depletion region. Okay, so here we have only the drain part, drain part depletion region are in the output side, so we are getting. Then we have the wire capacitance, the connectivity for sure will have some capacitance, and these capacitance are due to from the inverter to due to your gate and the source side overlap. If you just remember this one, we have this overlap. And why we have these overlaps? These are because of the fabrication non-ideality, and we can't avoid it. It will be there. So in one statement, your CL is comprised of the internal capacitance, which are due to this diffusion capacitance of your inverter. Okay, and then your wire capacitance and the capacitance from the external load. In this case, it is a second inverter, but there could be any other circuits also. So this is from the external node, and actually we can just combine these things because these are the external factors which are not in our hand. Anytime we are designing, we can design only our side, the part one. Load could be anything, right? So it is C internal plus the C external capacitance, which are our CL. So to reduce our CL, we have no control over the C external. Somebody will say, no, we have control. And yes, if we are designing this both of two circuits, but probably if we are designing or we are responsible for one of the block and some other block is designed by some other designer, so that time we don't have control, right? So that's why to reduce our delay, we mainly concentrate on this C internal. And C internal are due to your capacitance, which are coming due to diffusion in your inverter number 1. So that's why anytime we design or draw the layout of our circuit, our inverter, so that time we keep the minimum possible diffusion area of the drain side, so that we can reduce our CL. And if we have the control over this thing, then there also we do the same thing. For example, your CW, if you are having a long connectivity path between two circuits, which will increase your capacitance, so we try to reduce that paths. So these are very important points which you can just explain to your interviewer, how you can design an inverter looking into the performance or the speed of your inverter operation. So now we have done with CL. Now let's see about our equivalent of our PMOS or our NMOS. But we don't know anything about R equivalent, from where they are coming. You can derive your R equivalent formulae, but here I am not going to derive it, and for interview you don't need it also. So we have directly this formulae. So here we are just taking the previous formulae only, 0.69 your R equivalent and the CL. We are just replacing the equation of R equivalent here and we are getting this. So from here you don't need to remember it, you don't need to derive it, don't worry. And now we have the design parameter such as VDD, our W by L, and if we work on this thing, which will imply reducing our R equivalent or which will imply reducing our delay. CL is already done, we have taken care of it. From here we can't say anything directly for VDD because VDD is coming in the upper side and lower side also. So if we do some more simplification, then we will find out this thing. So from here, one thing we can for sure say is that if we just increase our W by L, which is coming in the downside, this expression is simplified to this. If we increase your W by L, our delay will reduce, and increasing your W by L nothing but reducing your resistance only, because your resistance are coming for your PMOS or your NMOS, right? And if you are increasing the channel W by L, that means you are giving more part for the current to flow. And from the intuitive only that yeah, if we increase our W by L, then our R equivalent will reduce. But here there is one catch. If you increase your W by L, right, so which means you are also increasing the size of your NMOS or PMOS. If you increase your size of your NMOS or PMOS, which will imply you are increasing the diffusion capacitance inside it. For example, this is your NMOS, right? And this have some L and it have some W. But if you increase it by twice the W, twice the L, which will imply the area of this diffusion area or this depletion area will also increase, and you know that your capacitance are directly dependent on the area. So that means on isolation, if we think yeah, increasing W by L will reduce our delay, but if we think about perspective of capacitance, then this is not the case. And from the analysis it is seen that if you keep on increasing your W by L, then we have our delay expression, right? So if you keep on increasing your W by L, your C internal will keep on increase, and which is called the self-loading, because you are actually loading yourself, your inverter only, by increasing its size. We need to do some mathematical calculation to arrive into a conclusion. So for that, let me do something. So I can write it as this: R equivalent C internal, I have just keeping it outside, so 1 plus C external by C internal. Now we want to make our inverter bigger or smaller. So for example, if our inverter W by L was equal to 2, we want to make it 4, 5 or something, we don't know. So let's keep it as this: W by L equal to S 2S. S is our multiplication factor. If it is 1, it is 2. If S is 2, it would be 4. So S is our multiplication factor, and you need to see it clearly that if you increase your S, your capacitance will also got increased by the same factor, and your resistance will get reduced by same factor. If you just observe it, you will find it out. But by intuitive sense also, that your capacitance is directly proportional to the area, but your resistance is inversely proportional to the area. So that means if I keep this S as our sizing factor, so your delay equation will be R equivalent. Your R equivalent will reduce by a factor of S. Your C internal will increase with a factor of your S, and then 1 plus C external will remain same, because C external we are doing nothing, we are just keeping focus on our inverter 1, because external we don't know, right? It could be designed by somebody else. So C external would be C external for now, and our C internal here also will increase by S. And now if you call this as TP0, the self-loading delay, because here we are getting the delay only due to our internal capacitance, not due to the external capacitance. If your external capacitance is 0 also here, then also you have this delay. So this is TP0, the self-loading delay or the unloaded delay of your circuit. So that means here also this S and S will get cancelled and we will be having 6.9 R equivalent C internal by 1 plus C external and S C internal. So you see we have done the sizing, right? But the internal delay, the unloaded delay is same as it is. So that means if you keep on increasing your W by L, which won't be reducing your delay, it will be the same. And it might reduce your delay if you have an external circuit also. To make it more clear, if you have a circuit like this, only the inverter, there is nothing loading it, this CL is only due to my internal capacitance, then you can do any sizing to your inverter. Minimum delay, which is a self-loading delay, would be same. But now in the case you have something here and then some other circuit here in the black box, then this CL is not only due to your internal capacitance but also due to the external capacitance given by that circuit, that black box. That time you might have some reduction in your delay if you size or increase the size of your inverter, of your input inverter. So now from this equation, it's a very important equation. You can see that if your S tend to infinite, your input inverter, this is our input inverter, is sized by infinite, right? That time this delay will go to 0, right? So that means if we can size our input inverter to the extreme, that time if we can load it with any other black box, that black box won't affect our delay. Our delay would be same as our internal delay only, or the minimum delay only. But we can't do it, right? Because silicon area is very expensive. And actually we don't need to go to infinity, but if we can go in such a extent so that our this C external term, by C internal term could go to 0 with a S, that also do our thing that yeah, we can be able to reduce our delay. So that's why we do the sizing. So that means to increase the performance of your circuit, your inverter, the input inverter, one thing you can do is just carefully do the layout so that our diffusion area or the parasitic capacitance is as low as possible. This is the one factor you need to do. The second factor is that when you have some load, some black box, that time you can use some sizing factor S depending on your area, and that is defined by how much performance you want. If you want a 10 gigahertz range, then you need to do the sizing accordingly so that your delay got reduced to that much. So that will be defined by the specification you want to achieve. This is two part. The third part is from this equation, actually not so clear from these two equations, but you just keep and remember that yeah, if we increase the VDD, the power supply, then also we can reduce the delay. And that is intuitively you can say yeah, if we have the more voltage, more VDD, then it will throw or it will feed more current, which will charge our capacitance more faster way. This is just a quantitative analysis, I am not going deeply. But with increasing VDD also have some concern, because we have a upper limit. After that, if we increase the VDD, it might create or burn out our devices. In general, we always keep our VDD should be greater than 2 VT. Actually, we have some graphs, or they have done some analysis. From there they have found that if you need to build a performance oriented circuit, then the VDD should be more than 2 VT. Actually it should be way more than 2 VT, then only you will get that performance. So now we have a question which is very common and very practical oriented question from an inverter. If you have ever designed the layout of your inverter and if you have extracted the result from that layout, you probably know that thing, and that's why they will ask you this question. If you in your CV, if you have something related to a layout, that yeah, you have designed your layout, and that is anytime if you have this is your input and you actually have a spike here in the output, then it will go down, and when it come here it will go a below down, and then it will settle down to 0. So why it is happening? What's the main cause of this?